In my last lecture, we discussed about the EPR paradox. Let us now proceed to discuss on Bell's inequality. David Bohm in 1951 showed that the hypothetical EPR experiment could actually be carried out using a pair of entangled spin-half particles. Then in 1964, using the EPR Bohm setup, John Bell constructed an inequality under Einstein's locality and reality assumptions. John Bell derived an inequality for a certain correlation function that has to be obeyed by any local realistic theory, and then he showed that for some experimental conditions the predictions of quantum mechanics can violate this inequality. The thought experiment considered by John Bell was not suitable for experimental tests. Clauser, Horn, Shimoni and Holt, so in short known as CHSH, removed this obstacle in 1969. They proposed a variation of the Bell inequality that was indeed possible to check by an experiment. These are the important references on Bell's inequality. The CHSH scenario is shown here, which consider David Bohm version of the EPR thought experiment. Suppose a third party, say for example Mukul, prepares two spin-half particles in some state, and then he sends one particle to Omlan, one spin-half particle to Omlan and another spin-half particle to Banti. Omlan can perform spin measurement. Now Omlan can perform measurement of two observables A1 and A2 on his spin-half particle. So typically the measurement of spin along two different directions. This observable A1 corresponds to spin measurement along a particular direction, say for example M1. M1 is a particular direction along which the spin is measured, and A2 corresponds to a spin measurement along an arbitrary direction M2. So M1 and M2 are actually unit vectors in 3 dimension. Similarly, Banti can measure two spin observables B1 and B2 on his spin-half particle. So B1 and B2, they corresponds to spin measurement along two different directions, say N1 cap and N2 cap. So these are another two directions in 3 dimension along which the spin measurement is done. As we discussed earlier, the measurement of these observables, that is A1, A2, B1, B2, can have the outcomes, measurement outcomes as +1 and -1 corresponding to the eigenvalue plus h bar by 2 and minus h bar by 2. So this observable can have this measurement outcome as +1 and -1. A2 also, the outcomes are +1 and -1. For B1 also, the measurement outcomes are +1 and -1. According to EPR, quantum mechanics is not a complete theory which can be supplemented by additional variables. The wave function or the state psi alone does not provide the complete description of the system. We need to specify some other hidden variables lambda along with this psi, so that the measurement outcomes for each individual quantum system are predetermined whether we make any measurement or not. In other words, if we could know the value of lambda along with the state vector psi, then we could predict with certainty the measurement outcomes or the measurement values of every observables A1, A2 B1 and B2. The measurement outcomes +1 or -1 we can actually predict with certainty if we know these extra variables, which is called the hidden variables, apart from the state vector psi. Then we can actually predict with certainty about these measurement outcomes. Consider an attempt to assign values to these observables A1, A2, B1, B2. So, we assign the values of these observables which are predetermined. We assign the values of these observables which are predetermined by some hidden variable lambda. So, basically we do not know, we have some ignorance about lambda, that is why this so we have some ignorance about the values of lambda, that is why we have probabilistic prediction. So that is why the quantum mechanics gives us the probabilistic prediction. So if we know the actual value of lambda along with the state vector psi, we can actually certainly predict, we can predict the outcomes with certainty. So we assign the values of the observables which are predetermined by these variables lambda, this hidden variable lambda, in this way, that is the value of A1 is equal to +1 or -1. So when lambda takes one particular value, it gives us +1, for another value it gives us -1. Value of A2 is similarly, we assign the values this way, value of the observable for Banti's measurement B1 is equal to +1 or -1, value of B2 similarly we assign the values +1 or -1. Actually these values VA1, VA2, VB1, VB2, they are functions of the state quantum state psi and lambda. So we should actually write it as V, value of these observables when we have given the state and the hidden variable lambda. So we are not explicitly writing this state vector and lambda everywhere. So it is implicit that if we have the information about the state and this hidden variable lambda, the value we can actually predict with certainty, the measurement outcomes, the value of the measurement outcomes we can actually predict with certainty. So when we assign a particular value +1 for the observable A1, it is assumed that Omland's particle had that value for this physical quantity A1 even before the measurement is done. So the measurement merely revealed that pre-existing value, that is Einstein's element of reality concept. Also, Omland and Banti are assumed to be far enough apart that performing a measurement on his system, that is Omland measuring on his system, cannot have any effect on the results of measurements on the other, that means on the measurement outcomes of Banti's particle, I mean Banti whatever measures on his particle on the other side. So this is the locality assumptions. The local value of A1, that is local measurement value of A1 remains the same whether we measure A1 with B1 or we measure A1 with B2 at a distance. So more specifically, the definite outcome, measurement outcomes, that is +1 and -1 for A1 and this +1 -1 for A2, these measurement outcomes are independent of whether Banti measures B1 or B2 on his particle at a distance. So according to the prescription of EPR, we have now assigned here the measurement values of these observables using locality and reality assumptions. So with these locality and reality assumptions, now we are going to do some simple algebra with the following quantity. With these locality and reality assumptions, now we are going to do some simple algebra with the following quantity, the value of the observable A1 times the value of the observable B1. These values are actually these predetermined values we have assigned, plus value of A2, value of B1 plus the value of A2 multiplied by the value of B2 minus the value of the observable A1 multiplied with the value of B2. So now we will focus on this quantity using the pre-assigned values of the measurement outcomes according to the locality and reality assumptions. So let us now see how many possibilities are there for the measurement outcomes for these observables A1, A2, B1, B2. So we will see all the possibilities of these measurement values assigned by some hidden variable model. So these are the possible measurement outcomes or possible measurement values for the measurement of this spin-half particle, for which the value of this quantity, that is, I have already written the value of this quantity for these measurement outcomes are, these are the possible values, that is, it sometimes it takes +2 and sometimes -2. So for all these measurement outcomes, the value of this quantity can be either +2 or -2. So the value of this quantity is either +2 or -2. The maximum value it can acquire is +2. It cannot go beyond the value of +2 according to this local realistic hidden variable model. So the value of this quantity that we obtain by assigning the predetermined measurement values is equal to ±2 that we have seen, where these values are fixed by some local realistic hidden variable scheme in this way, where these values are functions of the wave function and the hidden variable lambda. Now this quantity is associated with the following observable A1 B1 plus A2 B1 plus A2 B2 minus A1 B2. To obtain this observable quantity, what we have written over here, one can do this experiment in this way. The experiment can be actually repeated many times, and in each run of the experiment, Omlan chooses to measure either A1 or A2 in his particle, and Banti chooses to measure either B1 or B2, spin observable B1 or B2 on his particle. So for example, in one run of the experiment, Omlan chooses to measure A1 and Banti chooses to measure B1 for this observable, and in the second run of the experiment, Omlan can choose this spin observable A2 and Banti can choose the spin observable B1 to obtain this quantity A2 B1. So in this way they can obtain this value, and the experiment can be repeated many times. So taking an ensemble average over these measurements, the mean value of this quantity, I write it as ensemble average or the average value of this quantity will be equal to this provides us the measurement values, and we have to actually integrate it over a probability distribution. So measurement value times the probability distribution of the hidden variables, the rho lambda d lambda. So we have already mentioned that these values are function of the state vector psi and a hidden variable, a local realistic hidden variable lambda, psi and lambda, and rho lambda is a classical statistical probability distribution for this lambda, which depends on our ignorance of a more precise knowledge about the system. So the wave function alone does not provide us the complete description of the system, but we need to specify another hidden variable lambda, and that we have the ignorance about that hidden variable. So that is why we have to integrate over this probability distribution to obtain to get this average value here. Now we have already seen that this quantity cannot go beyond the value of 2, which we have already seen according to a local realistic hidden variable model that we have already seen. So this integral should be less than equal to this 2, and there is this rho lambda d lambda, integration rho lambda d lambda, and the this part will be 1 because total probability should be 1. So so this ensemble average or the average of this observable in the bracket, so I write it down here again, the ensemble average of this this observable A1 B1 plus A2 B1 plus A2 B2 minus A1 B2, this should be less than equal to 2. So this average quantity cannot go beyond the value of 2. Now from the linearity of this integration, this ensemble average or this average quantity can also be written as, this can also be actually written as VA1 VB1 rho lambda d lambda plus integration VA2 VB1 rho lambda d lambda plus integration VA2 VB2 rho lambda d lambda minus integration VA1 VB2 rho lambda d lambda, and this is the average quantity for this measurement A1 B1. So this is equal to the average value of this observable A1 B1, and this is the average value of this measurement observable A2 B1. So this is plus average value of this quantity A2 B1 plus the average of A2 B2, average of A2 B2 minus the average of this observable A1 B2, and this quantity should always be less than equal to 2 according to a local realistic hidden variable model. So this is the Bell's inequality. So according to a local realistic hidden variable model, this quantity, the average of A1 B1 average plus average of A2 B1 plus average of A2 B2 minus the average of this observable A1 B2, that should always be less than 2. This is the Bell's inequality, or better to say Bell CHSH inequality, Bell CHSH inequality. So according to the local realistic hidden variable model, this average quantity, average values of this quantity should always be less than equal to 2, which is this Bell CHSH inequality. And now we will go back to the quantum case, or in the quantum world what will happen, we will just now we will see. Let us now get back to the quantum world. So, we imagine the similar experiment, but in the quantum world here. Like previously, the Omlan and Bunty, they share an entangled state. They share an entangled state psi AB is equal to 1 by root 2 up down minus down up. So, Omlan and Bunty, they share this entangled state, quantum entangled state. So, these two spin half particles are now entangled. These two spin half particles are now entangled. Someone prepared this entangled state, and they one particle is sent to Omlan, another particle is sent to Bunty, and now they chooses to measure these observables. So, Omlan chooses this observable A1. A1 is spin measurement along z direction. So, z component of spin. A2 is equal to sigma x, and B1 for Bunty's particle, he is measuring spin along some other directions. So, B1, this observable B1 is equal to minus 1 by root 2 sigma z plus sigma x, and B2, the observable B2 is equal to 1 by root 2 sigma z minus sigma x. So, Omlan chooses the spin measurement along z direction, that is he sometime he chooses this sigma z on his particle, and sometimes he chooses to measure sigma x, spin component along x direction on his particle, and Bunty chooses to measure a spin observable. So, spin along, so this is a spin measurement along some particular direction, I will show you shortly, and B2 is the spin measurement along some other direction. So, this observable that is sigma z plus sigma x describes a spin measurement along some particular direction, and sigma z minus sigma x describes this describes also a spin measurement along a particular other direction actually. So, Omlan measures spin along these two directions, N1 and M1 and M2, and Bunty also measures his spin along two directions, N1 and N2. So, let me quickly show you that this corresponds to a spin measurement along a particular direction. Actually, this spin measurement along some arbitrary direction. So, we know that in spherical polar coordinate, and a unit vector can be written in this way, sin theta cos phi, unit vector along this x axis, plus sin theta sin phi j plus cos theta k. So, this theta and phi are the spherical polar coordinates, and this is a unit vector along a particular direction in that sphere, and the spin along this direction can be described by this operator sigma n. This will be equal to sigma vector sigma dot product with this unit vector. So, if we do that, we will get sigma x sin theta cos phi plus sigma y sin theta sin phi plus sigma z cosine theta. So basically if we choose this direction, this particular direction, if we put theta is equal to 5 pi by 4 and phi is equal to 0, then value of this quantity will be minus 1 by root 2 and the value of this quantity will be 0 and the value of this quantity cosine theta will be minus 1 by root 2. In that case, the spin along this direction n will be equal to minus 1 by root 2 sigma x plus sigma z. So actually this operator describes a spin measurement along a particular direction described by these two angles, that theta is equal to 5 pi by 4 and phi equal to 0. In a similar way, we can see that this operator, this spin operator 1 by root 2 sigma z minus sigma x, this describes a spin measurement along a particular direction where theta will be in the spherical polar coordinate, theta will be 7 pi by 4 and phi is 0. So basically this operator describes spin along some particular direction actually. So Amlan measured the observables A1 and A2, where A1 is a spin component along z direction and A2 is spin component along the x direction on his particle. Banti chooses to measure the spin observables B1 and B2, where B1 and B2 are the spin measurement along some particular directions, which I have already explained. Then for this entangled state, actually one can calculate the quantum mechanical expectation values. The expectation values of this observable A1 B1, the quantum mechanical expectation value one can easily calculate, and for this state where A1 is this sigma z and B1 is that operator, one can show that will give us the value 1 by root 2. I will show you that, and the expectation value of this operator A2 B1, this expectation value will be again 1 by root 2, and the expectation value or the average value, quantum mechanical average value A2 B2 for this entangled state will be 1 by root 2, and the expectation value A1 B2 A1 B2, the expectation value for this entangled state, and we choose the operator in this way, and this average value, quantum mechanical average value, will be minus 1 by root 2, resulting to this average quantity A1 B1 plus A2 B1 plus A2 B2 minus A1 B2. So we put these values here, that will give us the value 2 root 2. So quantum mechanical average value, average of this quantity we obtain, that gives us the value 2 root 2 for this entangled state. But according to local realistic hidden variable theory, we have seen that the Bell's inequality gives us a bound for this average quantity A1 B1 plus the average of A2 B1 plus average of A2 B2 minus the average of A1 B2, that should be always less than equal to 2 according to a local realistic hidden variable theory. So clearly we can see that these quantum mechanical predictions or the quantum mechanical average value gives us this value 2 root 2, which is greater than these two. So we clearly see that the Bell's inequality can be violated in the quantum case or in the quantum domain if we prepare an entangled state in this way and we do the same measurement along some cleverly chosen direction or particular directions. We choose A1 and A2 in this way and B1 and B2 in this way, and we see and we calculate the average values of this observable A1 B1 A2 B1 A2 B2 and A1 B2, and then we do the algebra that gives us this value 2 root 2, and that is experimentally also checked, or experimentally it was shown that in quantum case in fact this quantity violates this Bell's inequality. So this is the quantum mechanical result. So this is the quantum mechanical result which violates this Bell's inequality for particularly chosen observable. So this proves the Bell's theorem that a local realistic hidden variable model cannot completely reproduce the measurement statistics or statistical correlations of a pair of 2 qubit system or 2 level quantum system. If we prepare the 2 qubits in this state, in an entangled state like this, and we do measurement, spin measurement along these directions, then we can clearly see that this quantity violates this Bell's inequality. So here I quickly show how to calculate the quantum mechanical expectation value for a particular joint measurement observable A1 B1. So other average values similarly one can calculate actually. So the expectation value for that entangled state is, so we have to write the state in this way and we have to put the observables here. So this is quantum mechanical expectation value, and A1 we have chosen sigma z and B1 was this operator, Bunty's measurement on his particle. B1 was minus 1 by root 2 sigma z plus sigma x. So we just substitute it here. So that will be bra psi and sigma z. Actually there is a tensor product between these two Hilbert space, and that is 1 by root 2 minus 1 by root 2 sigma z plus sigma x, and then again this thing. Okay, so this is equal to minus bra psi, okay, sigma z tensor product sigma z minus 1 by root 2 sigma z tensor product sigma z, actually minus 1 by root 2 sigma z tensor product sigma x, this operator acting on psi. Psi is the entangled state. So let us first do this part and then we will do this part. So first we do this part of this operator acting on this entangled state, minus 1 by root 2 sigma z tensor product sigma z acting on psi, and we substitute actually the expression of the entangled state, that was 1 by root 2 up down minus down up. So when actually there are tensor product here also, so sigma z will act on this state, that will give us plus 1 with the multiplied by the up state. So this will be equal to 1 by root 2 1 by root 2, that is minus half, and sigma z acting on this will give us plus 1 times this state. Sigma z, this will act on this state, but when sigma z acts on down state, that will give us a minus 1 value, eigenvalue, because this up and down, they are the eigenstate of the sigma z operator. So that will make this plus 1, and then this state, and this is minus 1 by root minus half. So this, there is a minus sign here, so this will be half, and the sigma z when acts on this state, that will give us as a minus as 1. So and then the state again down and up will remain up, but that because of that minus sign, this will be minus. So finally what we will obtain, this thing, half up down minus down up. So actually this half can be written in this way, 1 by root 2 1 by root 2 times 1 by root 2, and this is again the same state, that psi, that entangled state. So this is equal to psi AB, that the entangled state shared between this Omlan and Banti. So the first part of this thing we obtain this, and the second part, if one apply, then one can actually easily show that that will give us this thing, that will give us this thing, minus 1 by root 2 some another state phi between the Omlan and Banti. This is another Bell state actually. This is the singlet state. This will give you another Bell state, which is up up plus down down. So this part of this calculation, when this whole operator acts on this entangled state, that will give us this thing. Now we have to do again the inner product of this brass eye here. So when we will do that, this brass eye will act on from the left on this, that will give us the value 1 by root 2, because this psi, this Bell state, that is the singlet state, is orthogonal to this Bell state, which is up up plus down down. So that part will give us the value 0. So effectively, I mean, at the finally we will obtain the value of this expectation value A1 B1 will be equal to 1 by root 2. So similarly, one can calculate the other expectation, quantum mechanical expectation values, which we have already written. So yeah, this is the way one can calculate the quantum mechanical expectation values.
Thanks for watching. If this is the first time you are visiting my channel, please don't forget to subscribe it and tap the bell icon to get notified for my new videos. Please comment below. Your thoughts and suggestions would be greatly appreciated.